So we are not going to standard hydrogen electrode. We would like to know what standard hydrogen electrode is. Well, standard hydrogen electrode is the electrode that is used as yardstick for measuring the electrode potential of other elements. So we use the standard hydrogen electrode as the yardstick, as the standard, and therefore standard hydrogen electrode is given electrode potential of 0 volts. So whenever we give electrode potential of any element, it means it gives us a measure of by how much it is bigger than that of hydrogen or below that of hydrogen. For example, the electrode potential of copper we are going to see later is 0.3 plus 0.34, meaning that it is 0.34 above electrode potential of standard hydrogen electrode. And that of zinc is minus 0.76 volts, meaning that it is 0.76 volts below that of standard hydrogen electrode. The question now is, how do we prepare a standard hydrogen electrode? To prepare a standard hydrogen electrode, what we do is to insert an inert platinum electrode, an inert platinum rod. The inert means it doesn't react so much. An inert platinum rod into 1 molar solution of ion of hydrogen. 1 molar solution ion of hydrogen. Meaning, when we say 1 molar solution of ion of hydrogen, we mean 1 molar solution of acid, because acid contains hydrogen ion. So 1 molar solution of hydrogen ion simply means 1 molar solution of acid, especially tetraoxosulfasis acid. So we insert a inert platinum electrode into 1 molar solution of hydrogen ion and bubble hydrogen gas into that solution, and bubble hydrogen gas into that solution at temperature of 25 degrees Celsius and the atmospheric pressure of 1 atmosphere. So when we do this, we have prepared what we know as standard hydrogen electrode. Remember, standard hydrogen electrode is the standard for measuring the electrode potential of other elements. Now that we have known what we mean by standard hydrogen electrode, whose diagram is on the board, we can now look at measurement of standard electrode potential. Measurement of standard electrode potential. Initially, I said that a metal ion metal system is a half cell that is somehow locked. A half cell, in the sense that it has only 1 electrode, which is the metal rod, and it is locked in such a way that, for example, when we talk about negative electrode, what we have there is electrostatic force of attraction between that negative electrode and its solution, which is positively charged. So there is an electrostatic force of attraction between them, which makes it impossible for the electron to move, which means it is like if the electron is locked. And when you go to the positive electrode, something like copper dipped into copper 2 tetraoxosulfasis, the copper rod is positively charged, while its solution, a solution of this ion, is negatively charged. So it is very difficult. There is an electrostatic force of attraction between that copper rod and its solution of ion, and which makes it impossible for the copper rod to pull electron from any other source, because there is already a force of attraction between it and its solution of its ion. So for us to make electron to move, we must connect one electrode to another, and when we connect a positively charged electrode to a negatively charged electrode, the next thing we do is to restore electrical neutrality at the solutions. We restore electrical neutrality at the solutions. Remember, for a positive rod, the solution is negative, while for a negative rod, the solution is positive. So we have to neutralize those solutions, make the solutions to be neutral. How do we do that? What we do is we use what we call a salt bridge to separate the two. We use a salt bridge to separate the two. A salt bridge simply contains either potassium chloride or sodium chloride, or ammonium triazonitrate 5. The importance of salt bridge, using salt bridge to separate the two solutions, is that the salt bridge, when it divides two solutions, one positive and one negative, the salt bridge will send positive ion to the negatively charged solution. It will send positive ion to the negatively charged solution, while some of the negative charges in the solution will move into the salt bridge. In such a way, by so doing, the negatively charged solution becomes neutral. Then on the other hand, the salt bridge will send negative ion to the positively charged solution. The salt bridge will send negative ion to the positively charged solution, and some of the positive charges in that solution will move to the salt bridge, and by so doing, electrical neutrality is also brought to the positively charged solution. So for us to get electrical neutrality in our solution, we use a salt bridge to demarcate the two solutions. In that case, the salt bridge will send positive ions to the negatively charged solution, and negative ion to the positively charged, and by so doing they neutralize each other. So when neutrality is achieved, when neutrality is obtained in the solutions, the electron can now be free to move because there's no electrostatic force of attraction holding it back. And again, the positively charged pole can now pull electron through the standard connection, the metal conductor that connects the two electrodes, because there is no force of attraction holding it back in this solution. So whenever electrical neutrality is achieved, the electrons in the negatively charged rod is now free to move, and the positive charge on the positive electrode will be free to draw electrons. Okay, so that is the first thing. Then I said it is not only salt bridge that can be used to connect two electrodes, to demarcate two solutions. We can also use a porous pot to demarcate them. A porous pot will allow negative charges from the negatively charged, negative ions from the negatively charged solution to move through the porous pot and enter the positively charged solution. So by so doing, the excess negative charge in the negatively charged solution will pass through the porous pot into the positively charged solution and neutralize it. So both of them become neutral because the excess negative charge will move away from the negatively charged solution and enter the positively charged solution where they neutralize each other. And by so doing, we now get electrical neutrality. And the porous pot works in a special way because it doesn't allow positive ions to move or the solutions to mix. So the porous pot will not allow the solutions to meet. Rather, it will allow negatively charged ions from the negatively charged solution to move through it and go into the positively charged solution and neutralize it. Now, to measure electropotential of any metal, what we do is to connect that electrode. If you are trying to measure the electropotential of zinc rod, what do? We connect the zinc rod with a metal conductor to a standard hydrogen electrode. Remember we said that standard hydrogen electrode is used as yardstick. So for us to measure the standard electropotential of any metal, we connect each electrode to the standard hydrogen electrode and they bridge their solution either with a salt bridge or demarcate their solution with a porous pot. Okay, so when we do that, we achieve electrical neutrality, and therefore electrons will begin to move from one to the other. Now, the apparatus for measuring electropotential of any element is shown on the diagram here. You can see the standard hydrogen electrode connected with a metal rod to the copper. This time we are trying to measure the electropotential of copper. So copper is dipped into copper 2 tetraoxosulfate solution, gives us copper electrode. And on the other side we have the standard hydrogen electrode, and the salt bridge divides their solution. And what is their solution? Remember, the solution of copper electrode is copper 2 tetraoxosulfate solution, while the solution of a hydrogen electrode is tetraoxosulfate acid solution. Now, when the electrode potential is measured in this way, because current, when an electron begins to flow from one electrode to the other, is equivalent to current being flowing, and the voltmeter in this circuit measures for us the electrode potential. That's the potential difference set up between the copper electrode and the hydrogen electrode, which is given a standard, which is given a electrode potential of 0 arbitrarily, electrode potential of 0 volt arbitrarily. Now, when we measure the electrode potential, the next thing is it going to be positive or negative? Is it going to be positive or negative? Well, it is going to be positive if electrons flow from the standard hydrogen electrode to that metal. So when electrons flow from the standard hydrogen electrode to the other electrode, that electrode becomes positively charged. Because the electrode potential becomes positive. I repeat what I said. If electrons flow from the standard hydrogen electrode to the electrode of that metal, then that metal has a positive electrode potential. But if, on the other hand, electrons flow from the electrode of that metal to the standard hydrogen electrode, then that the standard electrode potential of that metal becomes negative. So that is how we measure it. And for copper, in the case of copper, we see that our measurement will give us a potential difference of 0.34 volts. And in that case of copper, electrons are flowing from the standard hydrogen electrode to the copper electrode, meaning that the electrode potential of copper is positive. The electrode potential of copper is positive. So the electrode potential of copper now becomes plus 0.34 volts. But if we are measuring that of zinc with the same apparatus, that's connecting zinc electrode to standard hydrogen electrode, the voltmeter will read 0.76. The voltmeter will read 0.76. And the experiment shows that in this case, electrons will be moving from the zinc electrode to the standard hydrogen electrode, meaning that the electrode potential of zinc is negative. So that value of 0.76 volts informs us that the electrode potential for zinc should be minus 0.76 volts. So when electrons flow from standard hydrogen electrode to another electrode, then the electrode potential of that electrode becomes positive. But when electrons flow from the electrode of a metal to that of standard hydrogen electrode, then the electrode potential of that metal becomes negative. That example is that of zinc. Okay, so now we have finished everything about this. What they call it, standard measurement of standard electrode potential. So,